So our next speaker in the last block of the last day of the special session is Kennard, and he's going to tell us about torus representations connected with isometry groups.
Okay, thank you, Mike, and thanks to Ramina, Ramiro, and Carolyn for organizing. This is all joint work with Wiemeler and Burkhard Wilking at Muenster. So I want to talk about structure results and applications, but I want to talk about the applications first. That's what comes from geometry. So I'm interested in Riemannian geometry and specifically in positive curvature. I like the geometric definition of this, that if you have 3 points and you connect them by geodesics, the angle sum is strictly bigger than what you get in Euclidean space. That's by Toponogov's theorem equivalent to the usual analytic definition. This is a very strong condition, it seems, and I just want to remind people that in big dimensions, the only known examples for simply connected compact manifolds with this condition are the spheres and the complex and quaternionic projective spaces. So that's kind of a bummer. So what we do is, what Karsten Grove suggested in the 90s was to add symmetry to the problem. It fits with the special session theme as well. So to study this problem with symmetry, and this was motivated in part because the homogeneous case was actually classified in the 70s. This predates this formulation of the symmetry program. But there's many generalizations of homogeneous spaces. You can assume that the principal orbits have codimension 1. That's this so-called homogeneity 1 condition. You can look at quotients of homogeneous spaces called biquotients, or of homogeneity 1 manifolds, and there's various other generalizations. But those are the sorts of things that people look at. And so I want to discuss major developments here on one side on constructions and the other side of obstructions. So on the construction side, I'm kind of just mentioning just a few of the major results. So thinking about symmetry and positive curvature, homogeneous spaces, and things like this has led to new constructions of fundamental groups that weren't known to exist previously. Specifically, Shankar in '98 constructed examples that are not fundamental groups of spherical space forms. Also, this manifold that was just shown to have positive curvature in 2011, independently by Burkhard and Grove, Ziller. This is the last time a paper's been published with a new example in 10 years. And in the 10 years before that, 10 or 15 years before that, there were no others. So this is a rare feat, and it came out of studying homogeneity 1 manifolds with positive curvature. Most recently, this was mentioned earlier today. So Goethe, Karen, and Shankar completed a decades-long search for metrics with non-negative sectional curvature. So for that, you just take this strictly bigger than in Toponogov's theorem and put bigger than or equal to. So it's a weaker condition. And they showed that there's lots and lots of 7 manifolds that are 2 connected, but are not just spheres, that have non-negative curvature. And they show in particular that all exotic 7 spheres admit non-negative curvature. So that's on the construction side. These give us examples of things that we didn't know before. On the other side, though, there's been a lot of work, and these come in the form of obstructions. Another way to phrase this is that you start with a manifold with positive curvature. You add the assumption of symmetry, and then you see what you can say about the topology. So I'm going to summarize a few results along these lines, and so I'll put the assumptions here to be careful. So I'm dealing with compact manifolds, simply connected for simplicity. This notation is my abbreviation for positive sectional curvature, and I'm just reminding you of these orange examples that exist in large dimensions. So I want to focus on the case of torus symmetry. That's really, I think, where most of the results have been, although it's not necessarily the most interesting case, but it's the one I'm going to talk about today. So the question is, what can you say about its topology? So the first general result along these lines was Grove and Searle's result. They showed that if D is really large, D is the rank of the torus, and specifically at least a half of the dimension, then you get diffeomorphism rigidity. Specifically, they show the manifold is diffeomorphic to either a sphere or complex projective space. That's what I mean by diffeomorphism rigidity. Okay, so that's kind of the baseline. What I'm going to do now is list a bunch of results now where you relax the symmetry assumption, but then you can't prove as much. So you also relax the conclusion. So an example of this is a result of Fang and Rong, where they relax the symmetry assumption in this way, and then they show that you can nevertheless recover the homeomorphism type. And there you just get the sphere, CP, and you get HP2, but not the others. One step further was, this is a really important paper of Wilking. So he takes the symmetry assumption and cuts it in half roughly. And he's able to recover the homotopy type, and more specifically, the tangential homotopy type, if you know what that means. Those results are all really well known, but this one I just put up is also in that paper. So he relaxes the symmetry assumption further to n/6, roughly, and it's just in large dimensions again. And he can recover the rational cohomology ring. So what that means is he proves that the rational cohomology ring agrees with that of one of these three examples: a sphere, CPN, or HPN. The asterisk is because there's two leftover cases that paper doesn't rule out, but with our recent work, actually, you can cross out those examples. So this, it's fair to say, I think bulk of the work for this statement is in Burkhard's 2003 paper. Okay, so I'm coming now to two results I want to advertise. And for simplicity, I'll add the assumption that the dimension is even. And they're both, again, recovering rational cohomology. And the first result is this. So we relax the symmetry assumption from something which grows with n to something which is just a constant, specifically 7. So you should think of a manifold with T7 symmetry. So that's a big reduction on the symmetry. You know, we can't say very much just with that, but if we add a topological assumption to make up for that, specifically this assumption in green that the odd Betti numbers vanish, then in this case we can recover the rational cohomology of the manifold. So this result, the last time I gave a talk about this work, I discussed it with a T8 action. This is a slight improvement of that, and anyway, this is in this result is on the archive, just as of this month, I think. So that's a first result. So again, we relax the symmetry by a lot, but we have to make up for that by adding a topological assumption. So the main result I want to discuss today is similar. So we have, instead of T7, we assume a T9 action. Again, much smaller than this result up here. And what we do, instead of a topological assumption on the Betti numbers, we make a geometric assumption on the action. So specifically, to find what this means, that this assumption says that means that the torus action has connected isotropy groups, connected stabilizer groups. All right. So this is the main result I want to discuss today. Are there any questions, by the way? Feel free to jump in at any time.
So there are also some results without further assumptions, but the conclusions are weaker, right? Like something like positive Euler or.
Yes, that's right. That's right.
Okay.
Yeah, so in this same paper, sort of the main theorem to advertise there is that if with a T5 action and no additional assumptions, then yeah, we get the we can prove the Euler characteristic is positive. So that's exciting. It relates to the Hopf conjecture. But yeah, but I'm just focusing today on when can you recover the whole cohomology ring? Yeah. Thanks. So what I want to do is in one slide sketch the proof, leaving all the hard part for the lemma I'm going to state halfway through. So here's what you do. You have your T9 action, and I think I assumed this, or are we in even dimensions? We're in even dimensions, so in positive curvature, it's well known that you have a fixed point. So call it X, or pick one and call it X. And you look at the isotropy representation at the fixed point. So this is an orthogonal representation of a torus. These are pretty basic to write down what this looks like. But our assumption, and really the only assumption we need, is that this representation has connected isotropy groups. So just to be clear what I mean, if you take a vector in the tangent space and you ask, and then you have the induced action of the torus on the tangent space, you ask which subgroup fixes this vector? And well, it's got to be a connected subgroup. So the trivial subgroup, a circle, a two torus. We're assuming that you don't see things like finite cyclic groups, things like that. By the way, if any of you have worked with semi-free circle actions, this can be viewed as a generalization of that condition for products of circles. So in that sense, maybe it's somewhat natural too. So the main lemma, this is the hard part, but the main lemma that we need, and which we will discuss later, is this, that because of this assumption of connected isotropy groups, we can prove that there's a circle inside the T9 whose fixed point set is very big. And by big, I mean the dimension is at least 3/4 of the way up to the dimension of the manifold. So this is hard to prove, and I'm just going to take it as given for the moment. So so assume this, and then what's the big deal about that? So what's the big deal about the 3/4? Well, the connectedness lemma from Wilking's 2003 paper tells you a lot about the topology of a manifold with positive curvature that has a totally geodesic submanifold with small codimension. So fixed point sets of isometries are totally geodesic. So the connectedness lemma tells you things about the topology. And the 3/4, if you plug that into the statement of the connectedness lemma, it's exactly what you need to conclude that the first half of the cohomology of M, the ambient manifold, that the first half of the cohomology agrees with the corresponding groups of the submanifold. That's what the 3/4 buys you. And so in particular, if this fixed point component is a cohomology sphere, that means all of its Betti numbers are 0. Well, then the same is true for the Betti numbers of the manifold up to halfway. But then by Poincare duality, all of them vanish. So that's how you would lift the property of being a rational sphere from the fixed point set up to the manifold. So similar statements hold for CP and for HP. So what I want you to take away from this is this 3/4 assumption is sort of exactly what you need to reduce the problem to computing this circle fixed point component. So there's a part 2 of the main lemma, which says that you choose another circle from the induced T8 action on the fixed point component. And then you look at that fixed point component and you choose another circle. And altogether, the claim is that there's a T3, three-dimensional subgroup, whose fixed point set is also big, and specifically has dimension bigger than a third. All right. And again, I mean, what's the 1/3 all about? This is a longer calculation, but that's the critical level where if you know that fixed point component that I've colored in orange there, if that is a rational sphere, CP or HP, then by the connectedness lemma, so is the manifold itself. Right. So we have to prove that this orange thing is correct, has a correct cohomology. And to do this, we apply a slight refinement of the T5 theorem that is in this paper on the archive. So the T5 theorem, this is what Ramiro was asking about. The T5 theorem computes the rational cohomology of the fixed point components for a T5 action. That's almost our situation here. We have T3 instead of T5. And the theorem's not true for T3, but you can see what I've written here. It's true if you have this extra condition on the dimension. If the dimension is big enough, then you run the same proof. And basically this assumption takes care of one of the issues that would come up if you were proving it for T3 in general. And the point is, this does it for us. By this T5 theorem, this is like a T5 plus epsilon theorem. It's just a slight refinement for T3 actions. By this theorem, this orange submanifold, it has the correct cohomology. And then by the connectedness lemma, the manifold has the correct cohomology. So that's it for the sketch. The big question is, how in the world do you prove this main lemma? So I want to talk about it, but first I want to state really the proper formulation of the main lemma. So we're dealing with the representation with connected isotropy groups. I haven't really talked about what that condition buys us, but here's what it buys us. It says that there's a constant C of D, which is independent of the dimension of the vector space. You should be thinking this is independent of the dimension of the manifold, such that for any representation of rank D, for rank D torus, there's a circle whose codimension is small, whose fixed point set, okay, I really said that wrong. There's a circle whose fixed point set is very big, like we were hoping. And I'm phrasing this in terms of the codimension, so I want the codimension to be small. Okay. And, so what is this constant C of D? Well, first of all, it's less than 1. That's part of the non-triviality of this statement. But also, it's small. It's decreasing in the rank of the torus, and it decreases all the way to 0. And what this means is that with that part's actually not too hard. You can prove pretty easily that this eventually drops below a quarter. And for that rank D where it drops below a quarter, you get what you wanted before. A codimension less than a quarter, which is dimension bigger than 3/4. What I have,
Lee?
yeah, hi.
Hi, how are you? So this CIG condition can be described in terms of the weights?
Yes. Can it be described? Yes. In fact, that's how the proof goes. We're going to move there soon.
Okay. Thanks.
Yeah, thanks. Okay. And so this constant C of D, so to really get a T9 theorem, you need to know that this constant for rank D9 torus is a quarter. And we prove that it's exactly a quarter if you consider the maximum over all representations. So, so just to spell this out a little bit, so for a rank 9 torus action, if you apply this to the isotropy representation, then there's this fixed point component of dimension bigger than 3/4. That's what we needed for part 1 from the previous slide. And then what you do is you look at the induced T8 action on that fixed point component and apply the theorem. And because we know, because of the 1/3 here, you get a dimension bigger than 2/3 of that dimension. I'm not going to spell that out yet because you do it again to get your T3 fixed point set, which is again at least 2/3. And so if you can multiply fractions in whatever time zone you're watching from, you multiply these fractions, you get the 1/3 that you wanted on the previous slide. So this is just to show you that this gives us everything we need. Okay. So yeah, as Jorge was asking, what does this condition mean and how do you work with it? So the observation is that this really puts strong restrictions on the weights of the representation. So let me do a quick example of something which doesn't have this property. So here's a representation of T3. There's not that many irreducible subrepresentations. This would be like a first example if you were teaching about these things. It's pretty simple, but nevertheless, it has lots and lots and lots of disconnected isotropy groups. Here's 3 of them. I highlighted the 4th basis vector E4 in orange, and you can see because of the Z1 cubed, there's a Z3 which fixes that. And if you carefully compute, the isotropy of that vector is Z3 times a 2 torus. So that's a disconnected isotropy group. In the interest of time, I'll skip over these other examples, but you can compute these as well. These are further disconnected isotropy groups. So these show up a lot in most representations. So this hopefully suggests to you that this blue condition is very strong. But I want to be a little more specific about how could you have detected the existence of these? So what I've done here is write the weight matrix. So this is, if you look at the column vectors, these are the weights. So 1, 0, 0 corresponds to the fact that you're taking Z1 to the 1st power, Z2 to the 0, Z3 to the 0. You can see the columns correspond to the irreducible representations. And I've colored in orange and red a little bit to help guide your eye. What you see though is that if you take determinants of submatrices, like the 1x1 submatrix with the 3, that is determinant 3, that corresponds to the 3 components of this isotropy group. If you do the determinant of the red submatrix, that has determinant 2, corresponding to the 2 components here. And then if you take the last 3 representations, this one maybe you can do in your head, it's determinant 2, and again corresponds to having 2 components, specifically a disconnected isotropy group. So a formula is like a more formal version of our observation is that if you have a representation with connected isotropy groups, and if it's an effective, what do you call them, faithful representation, then you can put it in this standard form. It's just choosing coordinates and choosing a basis for the vector space. So you can make it so that it has the identity in the first D by D block. That helps things be phrased a little more nicely. So if you write your weight matrix like this, then the leftover part, H, is what's called a totally unimodular matrix. And this is probably pretty intuitive from the examples I just did. This means that every submatrix has determinant 1, 0, or -1. So totally unimodular that's the definition. So by the way, we knew this determinant condition for a long time, but we didn't know this was called totally unimodular. Once you know this is called totally unimodular, you can Google that phrase and find lots of literature about these things. And that's kind of how things happen. So so we have this condition, and the idea is, okay, we have a condition on matrices with entries the entries are just now zeros, ones, and minus ones. Let's try to classify what those look like, and then go back to the optimization problem about fixed point sets and codimensions. Okay, so think of this as a two-step problem. If you can produce a short list of totally unimodular matrices, then the optimization problem is probably not too hard. Well, we had a hard time with that, but then we, partly by discovering what these things were called, we discovered that these matrices were completely classified 40 years ago by Paul Seymour. This was a major paper, and it was more than that. There's actually still a long list, and I'm not sure that you can solve the optimization problem with that list. But there's more to that. What Seymour was studying was not just totally unimodular matrices, but he was studying classes of them under a natural equivalence relation. For example, if you swap two columns of a totally unimodular matrix, then all determinants are still 0, 1, or -1. Maybe you're changing the sign of some of the determinants, but you still have that condition. On the other hand, changing two columns of a weight matrix is just like changing your basis for the vector space. So somehow, like, that's okay. We should consider those things the same. Well, same thing for permuting the rows of the matrix. Same thing for negating the rows or negating the columns. This has to do with just changing your coordinates on the torus, or conjugating the complex numbers you have. There was a natural notion of equivalence. And there's another thing. There's something else you can do for a torus representation. I'm saying completely elementary things. You can precompose with an automorphism of the torus. And what this means for the weight matrix is that you're doing a row operation on the weight matrix. All right. If that's not obvious, it takes about a minute to write it down. So actually, row operations should be thrown in as operations for this equivalence. And what you find is that the equivalence class you get is representing something. The thing it's representing is called a regular matroid. All right. And so the big picture here is that these representations with this geometric property of having connected isotropy groups is exactly corresponding to matrices of this form that are totally unimodular. And that in turn is precisely connected. There's one-to-one correspondence with regular matroids. And this is a big deal because regular matroids are classified by Seymour. That's what Seymour was really studying. Am I going to is that my time actually? I'm a little bit, how much time do I have?
You are almost out of time, I think.
Out of time. Okay, then that's a good place to stop. I had a bonus slide. Maybe I'll put up. I'll just put this up. But so this is Seymour's classification, which won't make sense because I haven't told you what a matroid is. I haven't defined all these terms, but it might give you an idea that at least this gives us something to work with when we try to solve that optimization problem. Okay, so thank you again, and that's it.
Are there any other questions for the speaker? I guess they all got
we have some time for you to go through the bonus slide. So
bonus slide.
You can take 1 or 2 minutes and explain the proof.
If there's any young people here, that's a sneaky trick to get yourself more speaking time. This is really kind of a longer story, and the point is we had this big classification, but it was still a lot of work. And I just want to advertise a little bit. I actually am a big fan of these things called matroids now. They're really abstract objects, but they're grounded in your understanding of of linear algebra and graph theory. And so these things called graphic matroids are, you can think of them as matrices, things like incidence matrices you get in graph theory, where for each edge you get a column of the matrix and the entries tell you where which vertices it connects. And so the point is, like, this translates our optimization problem into one on graphs. And in particular, this problem at the end here, where you're maximizing over graphs and probability distributions. This is somehow the hardest part of the argument, but it's just by itself kind of an independent, kind of interesting question to try to do. So yeah, that's kind of, and like in the previous talk, there is one sporadic example, but that's no problem. Really, that's easy to throw away. Yeah, I think.
So Lee, just a quick question. You used the word optimization a number of times and that caught my attention. What do you mean exactly? Are you talking just about the codimension story to raise up to that?
Yeah.
Optimize the codimension based on the rank of the doors? Is that what you mean?
Yeah, so what happens is, yeah, the short story is this gets translated into a problem about graphs. And specifically, this D was the rank of the torus. So the case of where D equals 9 means you have 9, 8, 16 vertices. So imagine a graph on 16 vertices. Each vertex has 3 edges coming out of it. It's a trivalent graph. What we do is what we have to do is consider an arbitrary probability distribution on the edges. All right, so you put weights on the edges that add up to 1. And then what you do, so the graph is arbitrary and the probability distribution is arbitrary. And what you want to do is minimize the weight of a cycle. You want to find the cycle with minimum weight. So a closed loop in the graph where you add up the weights. And so you can, so that's the problem. You want to minimize over cycles, but then see what the worst case is, see what the worst graph.
And that minimum gives you the maximum ratio between codimension and dimension. Codimension.
Yeah, that's right. So like if this is a quarter, that means you get the codimension quarter like you need.
That C of D that you had, right?
That's C of D.
Okay.
Yep. Yep, exactly. Yeah. Hi, by the way, it's nice to see you.
Likewise.
Well, maybe we should thank our speaker again and then have a few moments before the next talk. Thanks, Lee.
Yep, thank you.